Welcome everyone, thank you for joining. My name is Shree Ramamoorthy and today's presentation is on designing a multi-PMIC Linux driver focusing on key decisions made for effective mainline submission. So a little bit about myself. I'm a software engineer at Texas Instruments based in Dallas, Texas. I'm a part of the power management integrated circuit team within our analog division, where I focus on Linux device driver development and customer GUIs. So about us, usually you'll hear this from our processors team, so I'm excited to bring this from our analog division. TI, Texas Instruments, and open source has a very much upstream first mentality where whether it's teams that have been established for years or my team that's been about 2 years old, which is awesome. We hit our birthday last week, so. This upstream first mentality continues regardless of your team. We really try to maintain that whether you're new or an expert, and I think that's something that's been fundamental in my learning process. So an overview of what's to come. First, we'll go into the background of PMICs, the PMIC Linux driver itself, and then focus on diving into the Linux patch series for cleanup and adding in new PMIC device support. And then we'll end with takeaways and reflections from this, I think, year-long project. So some focus areas and common themes that you'll see as I'm discussing all of the patch series is that this is my first Linux driver, and it is a relatively new software team where I'm the main Linux PMIC expert, so I've really focused on trying to gather as much knowledge as possible and really understand all of what's available. This project itself focuses on adding 2 new PMICs to an existing PMIC driver. We'll reference all of them, but there's a lot of similar names for this device family, so it's okay if you're a little lost. We'll also focus on how the hardware architecture design choices impacted the software driver decisions made, and really focusing on scalability. Not only am I adding in 2 new PMICs to this existing driver, but I really want to have the mindset of, if I have to come back and add in more devices for this PMIC family, will it be an easier venture in the future? So what is a PMIC? It's a power management integrated circuit that regulates and controls the power flow to various components like embedded processors, microcontrollers, and FPGAs. PMICs consist of LDOs and DC-DC currents, but I'll be referring to them as buck converters in this presentation. Some example features include watchdog timers, voltage monitoring, and power sequencing for our PMICs that are also used in our processor boards and like AM62L, AM62P, all of the AM62 whatevers, and phones, cars, and such. So why do PMICs need a Linux driver? Within our team, we focus on splitting into RTOS drivers and Linux drivers. So how do we differentiate who's gonna work on what? For RTOS, that really has to do with real-time performance and automotive safety requirements. That's when we defer to if this is going into our automotive applications. My colleague will work on an RTOS driver. If it's going into an industrial application, I'll work on the Linux driver. And the benefits of Linux are pretty amazing. There's a plethora of software frameworks and libraries available. The scalability is pretty amazing, and I do love open source because I feel like it really helped me learn by being able to see what are all the driver and feature options out there. So the PMICs are exposed as a device driver to interact with the kernel's power management framework, and these Linux drivers enable the system to trigger reboots, soft restarts, and low power modes. Also faster deployment, which is great for my timelines and projects. Moving into the typical PMIC Linux driver structure. So as you can see on the left in blue, for the I2C driver, it's primarily using the multifunction device, MFD driver. And then in red are the typical platform drivers that are included with our PMICs, the regulator, GPIO, and power button. For the purposes of this presentation, the power button driver ends up being the same for all of the PMICs, so we're not even gonna talk about it. And then in gray are platform drivers that are included based on the PMIC's device features. For the existing TPS 65219 driver, that's the PMIC where I'll be adding in the new device support. It consists of the MFD driver with the regulator, GPIO, and power button. So we'll be focusing on MFD, regulator, and GPIO. So let's compare these three PMICs. They're part of the same device family, and the way it's structured is on the far left, TPS 65219 is our original parent PMIC, let's say. In the middle, TPS 65215 has the most overlap with our original PMIC, and TPS 65214 has a couple new features. So all three of them have 3 buck regulators. 2 and 4 and 2 and 5 share 2 LDO, or they both have 2 LDOs, they don't share them, and 1 GPO. 2 and 9 has 4 LDOs and 2 GPOs. Something that is interesting, and we'll come back to discussing more, is that 2 and 4 has a GPIO whose output is configurable during device operation, and 2 and 5 and 2 and 9 have the same GPIO features. So we'll get into how all of this influences our driver decisions going forward. Now, the goal of this project was to prioritize code reuse without sacrificing user and developer readability. I really wanted to focus on simplifying the integration of additional PMICs to come, not only for these 2 PMICs, but just planning if there are future PMICs, how do I make future me's life easier, or the next PMIC developer. And on the left in this table, I really wanted to highlight the following patch series that we'll be covering. On the left shows the kernel version that each series was applied in, and we'll be covering 3 cleanup patch series, and then the last 3 rows are series adding in new PMIC support. Now, moving into the cleanup series, I really do want to highlight for the changes that will be discussed that these are very beginner friendly. I feel like if you're looking for a way to get your feet wet with upstream contribution and you want some straightforward ways to add in code, but really focus on how do you apply, are you sending everything in the correct format? These are some pretty good ideas that helped me get a good understanding of upstream. So for the MFD series, also all of the patch series are linked within the file. If not, you can just look up my name on lore. For the MFD cleanup series, I migrated the existing code to use MFD cell macros. I feel like this helps standardize all of the code before going in and adding the new PMIC support, or else that would have just been a mess of a series. I also removed any unused custom defined macros, like the last 2 defining voltage values. Those weren't used in the driver. Might as well get rid of them, so that way no one's trying to do what I did, where I kept searching, why is this macro defined? Why is it important? What is this here for? I also replaced any direct struct definitions like regmap and regmap IRQ chip data with just the header file instead, because as I was learning, I realized, okay, instead of just defining it, I'll just use the include file. For the regulator cleanup series, not only did I update the error handling to follow the more updated approach of using device error probe, but I also renamed the driver to follow established PMIC driver naming conventions, where it should be TPS 65 whatever dash regulator, but it was PMIC dash TPS, which didn't really align with what else was out there for RTI PMICs. I also removed the module alias to leverage the auto generation of the alias that was happening with the module device table. Then there were debug functions that were eliminated to optimize the production code, and that was all different patches for the regulator series. For the GPIO cleanup series, it was pretty straightforward. Instead of having custom GPIO direction macros defined at the top 2 rows, instead I used the existing kernel defined macros, because if it's there, why not use it? And now moving into adding new PMIC Linux driver support for TPS 65214 and TPS 65215. So we'll first start off with the MFD patch series, where the first two patches are pretty straightforward, adding in DT binding support. The third patch is a cleanup patch, removing an irrelevant function that actually didn't end up applying to the original 219 driver. So I guess that was also not only irrelevant, but a bug. But it was great because being a part of the internal PMIC team, I was able to find the systems engineer that worked on it and able to discuss, is this really needed? What value is this bringing? And then for the last two drivers, the order is pretty important. TPS 65215 is always added first, and then 214 builds on 215's patches. So the first hardware architecture impact that we'll discuss is that 215 and 219 have different status-based and acknowledge-based registers. Now, this might be something where you're like, oh, that's fine, it's no big deal. However, that required adding in an entirely new struct just for each new PMIC added to this. In my mind, I really wanted to have as many structs that supported all three PMICs within the same device family to minimize code churn and really highlight that not only are these part of the same device family, you can see that in the software itself. However, like I said, we are a relatively new software team, so it does highlight the importance of cross-functional collaboration in design, systems, and software going forward during the initial design phase. The second impact we'll discuss is that 215 and 219 have different bit assignments and meanings for the reg map, IRQ, sub-IRQ map for bits 5 and 6. So you can see it, the first two lines added show, okay, there are two different meanings for TPS 65215's bit 5 and 6. Great, that should have a pretty simple addition to the existing struct. However, that required adding in an entirely new struct just because there are two different bits. And so the ideal goal would have been, okay, add in or keep the existing struct that's there and have it work for all three PMICs in the same device family. However, from the hardware side, this seemed like the best case of IP reuse, but when analyzing it from the software side, there's actually a lot of improvements that could be made to support all teams. The third impact is that TPS 65219, the original PMIC, had its LDO3 mapped to TPS 65215's LDO2. And that was necessary for preserving regulator functionality and compatibility, but this resulted in multiple PMIC-specific structs added to the MFD driver, which may or may not have been avoidable during the initial design phase. However, this really does illustrate how one hardware decision can have such a big impact on our driver development. When I say 27 lines removed for clarity, a couple rows down, that just means all of those lines were repeated code from the TPS 65219 regmap IRQ struct. In my mind, it would have been great to have a way to do one common struct for all of the IRQs within the device family, and then have a device-specific struct with just this section pertaining to each 215 IRQ. Now, the whole goal of this project and the mindset I approached it with was to reduce the code churn as each new PMIC is added. However, as I was reflecting, putting together this presentation, and actually looking at the diff, that didn't happen for the MFD patch series. There was a similar amount of insertions and deletions when adding in the first 215 PMIC and the second 214 PMIC. And now, as I looked into it, the driving forces behind the code churn really do relate back to the hardware architecture impacts we discussed, where the PMIC-specific structs that were added to promote user readability ended up resulting in the same amount of code churn for both PMICs. Next, I also introduced a TPS 65219 chip data struct to hold the relevant PMIC information that would be handled within the probe. And I thought this was great because with so many different structs, you can really see what all do you need to add when you're adding in a new PMIC to the MFD driver. Okay, great. I need to make sure I'm accounting for the RegMap IRQ chip, MFD cell, the number of cells, add it to this chip data info table as shown below, and then this should result in minimal to no changes within the probe. That was my main goal for each of these drivers. If I had to add in a new PMIC, let's say 2 years from now, I would know exactly, okay, let me go to this struct, add in the relevant information, and the probe does not have to be messed with. For the regulator series, it's a similar structure where there is a cleanup patch that renames the structs to indicate whether it supports only TPS 65219, only TPS 65214, or if it supports all three PMICs by using TPS 6521X, which is going to be great for future users to know which functions support which PMICs with such a scalable driver. For the next two patches, for 215, there was one patch adding in the regulator resources support, and then the second patch adding in the IRQ support, and then those were combined into one patch for 214. Now this is where it gets a bit interesting. So as we discussed for the MFD series, there was about similar code churn for each new PMIC added. However, you can see that by the time all of the restructuring happened within the 215 patches, it resulted in about half of the diff amount for 214, which was my goal. And I'm really excited to see that going forward. So when it comes to restructuring the regulator driver, like I mentioned, my goal was to have little to no changes in the probe. I was very much fixated on that. It made more sense to just have to add in the PMIC specific information, and then the probe should be scalable enough to support all of it. However, I did attempt to abstract registering the regulators into one helper function and IRQ handling into another helper function. And the lesson learned was that that resulting diff was just really hard to read and did not pass kernel build tests. In order to get it to pass the build test, I had to combine it with additional patches, which defeats the whole point of a patch. You're supposed to make it into small, reasonable changes that are relevant and make sense. So the implementation that I did instead was to create one common struct for all the overlapping information, then have device-specific structs for the register, or I think it's the regulator description and IRQ handling, and then those are then handled sequentially within the probe. I'll then add a new PMIC to a chip data struct, not the exact same one as the PMIC or as the PMIC's MFD driver, but we'll go into that to show how it was easier for reviewers and patch organization. So this is an example of the chip data struct that was added to the regulator driver. And I really want to highlight in this example where you can see, okay, these are the two pieces of information that are required to handle all the common regulators to register, and then you can see in blue where all it was handled. Now what's great is this was the exact same implementation for registering device-specific regulators, just by switching which information to point at. And this is what I had originally attempted to abstract into a helper function, so I didn't have to do that repetition, but you can go see those old versions to see why it did not work. Now moving into the GPIO series, our last series adding in new PMIC support. The first one was pretty straightforward to update macro prefix names to indicate if this was 214 specific, 219 specific, or added in support for all, or supported all PMICs. Now, I really want to highlight what I touched on in the beginning of the presentation, and that's TPS 65215 has the exact same GPIO features as TPS 65219. When I originally wanted to add in support in the patch, I repeated so much code because it's the exact same. Why add in all of that driver support when a reviewer suggested to just assign the same GPIO compatible string in the MFD driver, and then you won't have all of that code repetition, which was something new that I learned. The last PMIC, TPS 65214, required adding in PMIC-specific get direction and change direction functions for the existing TPS 65219 driver, or 219 PMIC and 214. So why did those PMIC-specific functions need to be added? Why couldn't the same function apply to both PMICs? This is something that baffled me a bit as I was trying to figure this out. And the different GPIO direction registers and bit assignments for the input and output values are all different. There's different register addresses that need to be accessed, different bit position numbers that need to be accessed. Not only that, the input and output values input and outputs were assigned to opposite values for the PMICs. In red, 0 corresponds to an input for TPS 65214. In blue, TPS 65219's output value is assigned to 0, which then required so many different variations. It made more sense to separate all of that into PMIC-specific get direction functions. The second hardware architecture impact will explain why change direction functions were needed for each PMIC. So as I mentioned previously, TPS 65214's GPIO has a configurable output during device operation, where TPS 65219, the original one, did not. So, okay, great. GPIO config can be changed in red, and that happens if in blue that bit position is set to 0. Great. Because they have such different feature supports for changing directions, originally I had it in one function with nested if statements, for loops, and it really just was a cleaner approach to separate them based on which PMIC was being handled at the time. Something I do want to highlight is 214 has 2 pins. TPS 65215 and 219 have 3 pins. Great. Now, the GPIO mapping from Linux to PMIC really baffled me because I was not familiar with how it all worked in the beginning. And I didn't know I had to maintain whatever mapping existed to support backwards compatibility. And the existing driver mapped Linux GPIO offset 0 to the PMIC GPIO pin. Great. I did not understand what all was happening because there weren't any comments. I wasn't a part of the original series, and I was just lacking a lot of context as I'm also trying to learn this topic. So I really want to highlight that I reached out to the original author of the series, Jonathan Cormier, to gain context on mapping, which also resulted in one-on-one patch reviews before submitting the next upstream version, because he's the expert. He wrote the original driver. It was great to actually get all of his context and discuss different ideas before submitting it, because in the end, the original author should really approve of the changes you're making to their work. So in the end, the result was the existing code calculation done did apply to all 3 PMICs, even though they have different pin counts. I added in comments explaining this mapping for future developers and users so they don't have to reach out to Jonathan or I. And now I have a corrected understanding after gaining context from the original author. Some takeaways. As I was planning and trying to figure out the best approach on, okay, I'm gonna do my first PMIC Linux driver, I wanna do it well, what all is out there? And so I looked at drivers that had similar features I wanted to add, similar ideas, to understand the precedent that's out there for upstream process and acceptance, to understand the possible feature history, And I also want to note that it's important to take note of what year the driver was written and modified, because that may involve outdated functions or approaches. So it's great to understand the context, but maybe don't implement it exactly. This is probably a given that everyone's heard, but to think about the patch from a reviewer's point of view. I was so head down trying to really understand and develop the driver in the first place that it took someone saying, hey, if we weren't the developers and we don't have any of the context, what would you say? So my mentor always says to put my maintainer hat on and actually review my patch as if I'm a reviewer, a maintainer, and what would I give as feedback if this were someone else's work, which was really humbling, but also exactly what I needed to hear in that moment to understand how to best approach organizing all of, it was 6 series with about at least 3 patches in each one. It was a lot to figure out and organize. So would definitely recommend putting on your maintainer hat. I also had learned in the process of upstreaming different subsystem drivers that there is a precedent of the MFD and regulator subsystem maintainers accepting a series that combines both patches, so that way you can get it accepted in one cycle instead of having to wait a couple of weeks after your MFD patch series is accepted, and then submit your regulator driver, which is what I did. And to help with the timeline, I wish in hindsight I had submitted it in one series and asked for an immutable branch to be created. And that is something that really I'm gonna use when planning in the future. Actually, another idea I had, maybe there's a way to implement this, but as I was racking my brain and trying to see what all was out there, I could not figure it out. For the regulator resources and RegMap IRQ structs, like I had shown on why there was similar code churn for adding each PMIC in, I couldn't figure out a way to nicely and, cleanly structure a common struct for the regulator resources that all overlapped, and then adding in a device-specific struct for those PMIC-specific regulator resources. And I wish that was the way I had implemented it. If there is a way out there, I'm putting it out for advice and feedback. Same with the RegMap IRQ structs. So that's also an idea that, okay, I did this for regulators. It was great. It reduced the code churn for adding in TPS 652 and 4. How can I do that for the MFD driver? Acknowledgements. I want to thank my manager, Michael, my mentors, Praneeth and Vishal, Andrew Davis, Jonathan Kormeyer, Dhruva, Brian, maintainers, and many more. This was a pretty long project, but I'm guessing in the grand scheme of things, this is typical. And it took a lot to plan, develop, test, and then fix bugs. So a huge thank you to everyone. And moving on, thank you for joining. This is my first Open Source Summit presentation, and I would like to open the floor for questions, advice, feedback, and then if you want to connect as well, my LinkedIn is there. So thank you so much. Any questions? Yeah. Yeah. Oh. It might be for the recorded session, or. Yeah. Okay. I'll repeat.
So you've seen how fields that change a little bit is really annoying.
Mm-hmm.
No good reason, right?
Mm-hmm.
Don't bring any features. Have you had any chance to speak to the hardware team to avoid that in the future?
So the question is, certain bits that are changing are really annoying for software development. Have I had a chance to speak with the hardware team? Absolutely. I not only have discovered this when developing this PMIC driver, I also have developed all of our customer GUIs for the last couple of devices and noticed the same things as well. There are certain minor differences that come from just humans writing it, where they'll use a colon instead of an equal sign, and that throws off my entire script. And there are certain nuances that you can tell which systems engineer wrote it. And so coming in as the new software team, we had this fresh perspective of all of these non-standard standardizations that were occurring. And I think I brought this up with my manager and our team. And then in an attempt to just standardize a couple of things for the software team, we actually started an entire restructure of how we're approaching assigning certain bit positions, doing the naming, and really changing it not only at the software level, but at the design and systems level. Because as we were discussing it with different teams going forward, we realized, oh, everyone also has some slight annoyances with different variations that no one really has discussed, or let's say you discuss it, we're all busy people. It's hard to actually address it in the first place. So we're starting to work on that in stages to help prevent that in the future or minimize it as much as we can. Thank you. One of y'all too?
Thank you, Shree, for your awesome work. Do you have any plans for the watchdog functionality in this PMIC?
For the what?
Watchdog functionality.
Oh.
Do you have any plans?
Yes. Which, do I have any plans for the watchdog functionality in these PMICs? So as I have been going through it, I have noticed that there is some missing support, not only for the watchdog, but for some patches that you will see from me in the future. So I've put together a project of missing aspects of our PMIC drivers that are very niche, and while I've caught them, I want to make sure I address it not only for the PMIC it's called out for, but for all the PMICs that are out there, if I can test it. So there's a lot of PMICs, there's a lot out there, not only for some GPIO features I want to address, but also watchdog capabilities, and I'm slowly putting together actually a PowerPoint on a lot of typical PMIC Linux questions on how to control certain things or what user space commands are available. I feel like the information is pretty scattered, but now that we have a centralized PMIC software team, I do want to address those in the future. Thank you. Yes.
You mentioned this took a long time. What was the total time frame for all these series, and what was the average ratio between actual development and getting it into the kernel?
The question was, this took a long time. What was the average time between starting it, getting it to the kernel, and getting it accepted, right? I actually put together a breakdown for this for my manager, and he said, don't include it in my mid-year review. So I think I have the document somewhere. I broke down how long it took from start to finish for the MFD cleanup series, GPIO cleanup series, and the regulator cleanup series. It was all very detailed, which I think is why it was not advised to put this in. But maybe if we come back, I can try to find it. I think I remember, let's see. It depends. It depends on each series. Total time, I definitely started April of last year, but it also has to take into consideration I was working on a couple other projects at the same time, and at some point I went on vacation for 2 weeks during a merge window, which I need to reconsider. So at least about a year, I'd say, and then we go from there. Yeah.
So you mentioned you do upstream first. So what are your customers doing while you are doing the upstream? What code are they using for the driver?
So the question was, I mentioned that TI is very upstream first. What are customers doing in the meantime? And that's actually something I had a question about when I first started. How are we supposed to even upstream this if the device isn't RTM'd and available online publicly? How does this exactly work? And I took the advice of how the processors team operates in terms of, let's make sure that the code is ready by the time customers need it. Let's upstream it even before it has released to market, but we'll upstream it with a simplified data sheet or TRM, whichever, they're basically the same. And then ensure by the time our customers need the product, it's at least submitted, at least started the upstream process, and we have something to refer them to. And then from there we can say, this is a work in progress, this is not available in our SDKs, but here's the work, you can see that it's on its way, if not already ready.
For example, we have PMICs that go with our processors, so most of the times what they work on is the drivers for those PMICs, and then customers can use that as a template if they want to change the PMIC in their product, and they can develop software based on that.
Usually our PMICs are tied with our TI processor SDK releases. And so usually when I'm putting together the drivers, I'm putting it together in terms of the SDK timeline. So that way most of the customers will know that it's ready with that SDK. And so whenever they're going through their code freeze deadlines, that's the same deadline I get. So simultaneously, while I work for the PMIC team, I'm also working for the processors team because it's a joint effort. Any other questions? Yes.
We have time. I can't help but notice this is a Linux driver, and you have recently been choosing to put quite a few shared resources behind the DM firmware T8 SCI interface. How do you decide on putting shared stuff behind DM firmware or behind just a plain Linux driver? Is the question clear?
Yes, but I don't think it has to do with.
So, do you have any particular devices in mind?
No, I mean, not particular. I mean, talking about PMICs, you can expect other firmwares that want access to that. So you might want to put it behind the DM. I'm not saying it's a good idea. I just don't understand when you decide to put something behind the DM and when you decide to just do it from Linux.
When we just. Oh, I'm not gonna. I don't know the answer. But Dhruva, if you want to just come up here so it's easier to speak into the microphone, that would be helpful. Thank you.
All right, so the question has been put forth that we have this entity called as a device manager, which is a firmware entity. It runs on like a Cortex-R5 core, and Linux runs on like a Cortex-A core. Now, when do we make the distinction to put things inside the device management firmware, and what do we put inside Linux? So it's a valid question because we do a lot of power management inside our DM firmware, but that power management entails very generally to the, it's very SOC specific. So imagine that DM firmware is generally meant to do things related to power management inside the SOC. So everything from toggling the power state drivers to controlling the clocks, clock frequencies, those kind of things. You know, controlling the PLLs and those kind of things are done in the DM. But when there is an interface sitting outside, and our DM firmware is usually common distributed across to our customers. So most of the times it's easy to customize Linux. Like as a SOM vendor or as a, you know, for example, BeagleBoard, they're going to make their own parts with their own PMICs. So now they can't go and rebuild the DM firmware every time, right? So it's much more easier to customize Linux. It's a matter of changing the DT, for example. So that's how it makes it easier.
Any other questions, comments? No? All right. Thank you so much for joining, everyone.